Hello, welcome everybody to the new video. This is the second video in the book reveal series, and today I would like to talk about the technical contents of the book. In case you have no idea what I'm talking about, I'm doing a preview of a book which my partner Jan Hansen and me wrote together called EMC Simulation of Electronic System, which will be published in Spring and Nature. You can see the homepage here of the book. It has been slightly delayed till the 23rd of January. So unfortunately, there was some unforeseen circumstances with the publisher that we cannot do anything about. But we hope that this is the final release date and the book can be released on this date. What I have right now is, this is not actually the official manuscript. It's still the working manuscript that we have been working on. But I would like to give you an idea of the content. So we will go through the table of content and explain a little bit what will be the content inside the book. So today I will go through the first 9 chapters, which is half of the book, and in another video, which will be released later, I will go through the last chapters of the book. So I had already published a first video about the general ideas of the book and how we came to the idea to write the book. And most of these general ideas are in chapter 1. You see, we give a general overview of EMC modeling. What is the book about? What is the methodology of simulation we are actually employing throughout this book? A few words about simulation accuracy and the comparison of simulation versus measurement. We are not treating this in detail. It's a very complex topic, and the idea of the book is more to give you a tutorial how to set up simulation model. And talking about how to compare them to measurements would probably fill a large number of other pages. So in case you have expected this will be not contained inside the book. The first one is really a tutorial. We give an overview of the application examples which are presented in the book, and there are many application examples throughout this book. We wanted always to use examples to illustrate the simulation methodology and illustrate the effect of settings on the simulation. Hardware and simulation times. So this has been all simulated with a desktop PC I had at my home, and the software package is CST Studio Suite 2024. So that's just the introduction. What's now interesting is really what are the contents, and the idea of building the book. As you can see, like chapter 2 is called circuit component models. Circuit simulation is a big part of the book, and a circuit simulation is one ingredient of the whole EMC simulation. So this is why we need to start introducing what are circuit component models. And we start by an introduction, and in case you need some help understanding circuit components, we think that actually interpreting a circuit component as an impedance is a very good idea, because an impedance for an electrical engineer, the impedance is some kind of natural value, right? You know what means 5 ohm, you know what means 5 milliohm, and you know what means 5 mega ohm. So this is a way how we could interpret circuit component models. We do, of course, all the simulation using the SPICE engine. Might be another choice, like for example Simulink, but of course for analog simulation, which we are doing, SPICE is the method of choice. Then after giving this kind of also introduction, we start listing models. So source models. How do we model a source on a schematic? We have the simple voltage and current sources. What do a signal, a trapezoidal signal, mean in terms of frequency content and in terms of time domain content? And we discuss analog noise sources, which are transistors and diodes, digital noise sources, which are typically modeled by IBIS models. So everything is circuit schematic. Then moving on from the sources, we of course would like to characterize also the coupling paths, because in the book everything is divided into, as you can see, source, coupling path, and sink. And describing the coupling path, of course, depends a lot on the electrical size of the coupling path. If you have an electrically short coupling path, we can use lumped models, and we typically use lumped models, RLC models, for discrete components. But if your coupling path is no longer electrically short, it's electrically large, we have to move to the so-called network parameters, as what you see in 0.2, 0.44. It's network parameters. Most of the time it's S parameters, but could be also Z or Y parameters to describe something. And network parameters are not using S parameters in a SPICE circuit is not standard. That's why we explain a lot how to connect S parameters into a SPICE schematic, because a network parameter model which contains ports works differently than a standard SPICE model. And there's a nice description on how to do the connection, because I know from the past that this is often confusing to people. Then we talk about sync models. How do we model a sync, right? Where do we measure the signal? So generating sync models like resistors, then describing listens, antennas, and will not be covered in detail here because they will be covered more in the radiated emission section. And then we discuss the EMI receiver, which is kind of post-processing. And the last two sections is linearity and time invariance of components, because in case your component is linear and time invariant, you can also do a frequency domain simulation, or what we call as an AC simulation in SPICE, so explaining when this is possible. And finally, there is an advanced section, and many of the chapters contain an advanced section. And in the advanced section, we discuss how to get back from a S parameter or Z parameter block onto an RLC description. So this is something which can come in handy, but not necessarily what you need to do every day. The next section now is the next chapter, chapter 3, deals with EMC assessment using a pure circuit simulation. So we don't have yet any electromagnetic simulation. We just use the circuit model to calculate EMC of a buck converter. So the whole chapter dealing with the buck converter. And of course, we need to talk about how to get from a functional circuit into an EMI circuit, right? How do we get from a design, from a schematic which has been defined for the design of the buck converter into a schematic which can calculate EMC behavior? And then we do this step by step. We add component parasitics, we build the schematic over and over, and then we discuss how to get to the component, to the parasitic values of something like a signal trace or a plate. And we give really analytical equations. So instead of, now at this point, it's we still don't use the 3D simulation methods. We tell them, okay, if you want to have a parasitic value, you can also calculate it from some analytical equations, of course with limitation, but it's possible. Then we assemble everything into a lumped model of this DC-DC converter, of this buck converter, and analyze it in time and frequency domain. Once this is done, of course, we discuss what are the limits of circuit simulation, because there are definitely limits. For example, like for arbitrary geometries, there are no analytical equations and so on. We discuss shortly how to avoid common pitfalls, what are the typical ways, what needs to be what you need to take care of to make sure that your circuit simulation is correct. And in the advanced chapter, we describe how actually a transient circuit simulation, basically the idea of a transient simulation inside SPICE, which is actually quite complex. You don't need to know all these details, but in case you are interested, you can go through these topics. Then the chapter 4 deals now with electromagnetic field computation. We call it EM computation, and we introduce it going, of course, the circuit simulator, it did solve Kirchhoff equations. The electromagnetic field simulation needs to calculate Maxwell equations. So we give a very short introduction to the solution, and then we go step by step what is actually required to perform our electromagnetic field computation. We need to have a geometrical input. We need to bring in the geometry of the DUT we want to analyze. Once the geometry is imported, we have to talk about mesh. We have to generate a mesh over the geometry. We discuss why a mesh is required, what is the so-called mesh quality, what is mesh adaptation. Once this is done, we discuss materials, right? You have to model a material of your DUT, and there are different material models depending on what requirements on the materials are. So we compare like PEC, lossy metal, and volumetric conductors. We introduce dispersive materials and keep the nonlinear materials short at this point because this will be treated later. Then we discuss boundary conditions. How do you limit your computation domain? We discuss sources, because depending on the type of solver you use, your different choices will be there. And we explain just shortly a little bit of theory, how to get from the fields which are calculated by the electromagnetic solution into voltages and currents, and have another section, avoiding common pitfalls in EMC simulation. Then we start comparing two different field computation methods, namely time domain and frequency domain methods. Basically, time domain methods, FIT and TLM, and frequency domain methods as a FEM, finite element method. And we explain the basics, how these methods actually work, how these methods solve Maxwell equations, and how to determine the right solver choice. Which properties of the model we want to simulate determine which solver will perform better. Then, after giving this as an overview, we do really a comparison. We compare solver performance in terms of electrical size. This is FIT versus FEM. So you can see, depending on the electrical size, which is one of the properties would determine the solver choice, how the solvers perform. And in the second comparison, we compare both time domain methods, FIT and TLM, to each other. In the last part of the chapter 4, we talk about the spatial discretization, basically a few images, how the field is allocated on the grid. Not necessarily a must know, but maybe interesting again for the reader. Then we talk about the field allocation in the FEM and give a short overview why the method of moments is not used in the book. Finally, another advanced section is the time discretization, because it's important to understand when we solve Maxwell equation, right? We need to resolve the spatial, we need to resolve the space, and we need to resolve the time with a discrete method. And this is done differently in the time and frequency domain method. So that's advanced knowledge, which not necessarily need to know. In the next chapter, we built this book a little bit like a EMC book would be defined, right? In an EMC book, you always have the near field coupling, then you have the far field coupling, and that's exactly the idea here. So the 5th chapter is now talking about near field coupling. It's not this definition of near field and far field on the distance. It's rather, it's not like an antenna space. Where is the near field? Where is the far field? It's rather like when we talk about near field, we can apply static or quasi-static approximation to the solution of the Maxwell equation. So this chapter is a little bit special. It's more kind of teaching chapter to get you the idea of the workflow. Like we use a electromagnetic simulation to calculate the properties of the coupling path. Later on, we will not use much of this, what is done in chapter 5, but it's something which is kind of teaching the thinking. And what we do is we have this decomposition of the EMC problem, right? In source, coupling, path, sink. We do such a decomposition in terms of the circuit model and then show how the individual special solvers. So galvanic coupling is, of course, just a stationary current. Capacitive coupling is an electrostatic calculation, and inductive coupling is a magnetostatic calculation. So we do it really step by step. We have a model. We show how we can extract from the model the properties of the coupling path and really manually use this on a circuit schematic. So this is really an exercise. It's not like daily usage, but it gives you an idea on how the values or how the properties extracted from the EM model can be used on the circuit schematic. So again, for galvanic, for capacitive, inductive, and all are done. So this is done all on PCBs, actually, all these examples. So here, the capacitive example is quite interesting, where we, for example, look at the common mode voltage, which is generated on a listen due to a clock signal. A quite nice and interesting comparison. So finally, in the last part of chapter 5, when we still talk about near field, so we had basically we have separated R, C, and L, right? Galvanic, capacitive, and inductive coupling. And then we say, okay, there is a method where we can do the RLC extraction in one go from the one and the same simulation model. And this is a partial RLC extraction. It's a very common way where we, instead of manually extracting, we build a SPICE model of the coupling path, which contains all RLC elements. And this is often done with the so-called concept of partial inductance. So that's why the partial inductance is explained first. Then we talk about partial resistance, partial capacitance, and apply this to a half-bridge module, okay? So this is the very common way for power electronics application, actually, because in power electronics application, when my frequency isn't that high, my coupling path is typically electrically short and can be described by RLC model. Once this is finished, we move now to chapter 6, which is coupling path near and far field, which basically means in our terminology, this is the full wave simulation. We move away from this simulations or from the solvers. We did some approximation. We now solve the full Maxwell equation. And this is now a lot of explanation in this chapter come down to how to evaluate electromagnetic fields. How can I measure actual electromagnetic field? All putting it in a different context. What does all these fancy, colorful pictures mean, right? So we talk about field probes, a position where you measure the field inside the computational domain. We have a small radiated emission example, very, very simple, but explaining the usage of field probes and interpreting how the fields behave. We talk about the accuracy of field results, signal duration for time domain simulation, the size of the computational domain, the effects of boundaries. And then from the field probes, we move to the field monitors, now to the colorful pictures, how to get actually values, not only inside the computational domain, but I mean, sometimes this is called the far field results, like for antenna far fields, but the same also for radiated emission. Sometimes you want to calculate fields which are not in the computational domain, how this can be performed, what I call field results outside of the computational domain, which are performed by a near to far field transformation and so-called far field probes. Then we have an application example of a coupling of a twisted pair wire into an antenna. And in chapter 6, 7, actually, we now discuss how to couple the full wave solvers to a circuit simulation, right? Previously, in the previous chapter, in chapter 5, we have done RLC extraction and we use RLC elements to describe the coupling path. When we use a full wave model, it's no longer RLC elements. We are using S parameters blocks. And these S parameter blocks can be also connected on the schematic, of course, to connect, for example, a source. So this is like complementary basically to the section 244, where we discuss the network parameters, right? Here we talk general about network parameters and how they're connected on a schematic. And here we do it really particularly on the network parameters or the S parameters model, which are extracted from a full wave simulation. We discuss when to use lumped elements and ports, how actually interpret voltage and current when we probe voltage and current on a circuit schematic. What does that mean for the voltage and current in the 3D model? Then also RLC extraction away from the full wave solvers, how you get RLC values from S parameters, and how we use combined results to calculate resulting fields, how the circuit actually can give back the information to the electromagnetic, to the full wave electromagnetic solver and calculate a resulting field. On the advanced side, we talk about far field monitors that are not used much. We mainly stick to the far field probes in this book and the concept of field sources. It's explained briefly that this exists. We don't use the field sources also throughout the book. Chapter 7 now, I think up to here, a lot of the basic knowledge has been laid. And now we move on a little bit to something more application-oriented with the shielding effectiveness. We start calculating shielding effectiveness. Actually, shielding effectiveness is one of the few chapters where we don't need much of a circuit because we can compare a simulation with and without the shield. So this is a kind of, let's call it simple and very much EM-focused chapter. So we talk about what is shielding effectiveness, and we study shielding effectiveness planar material just to connect them to zero, to give you an idea what is the accuracy you can reach with the simulation, and how can we compare theoretical values obtained for shielding effectiveness to the shielding effectiveness calculated by a simulation. Then we go through this electric field for a plane wave magnetic field, and then we use a loop excitation because magnetic field from a loop, of course, can penetrate through a metallic material, and we studied these cases. Then we have an example which is magnetic shielding in a vehicle. So we have a more complicated cut geometry and discuss the magnetic field generated from a pair of cables inside a more complex setup. And finally, more, this is a rather low frequency application, magnetic field shielding. This is more a high frequency simulation where we study the shielding effectiveness of our enclosure and compare like plane wave illuminating the enclosure and putting a source inside the enclosure. We compare them. So many of the examples in the book are trying to compare different approaches to each other to let you choose which of the approaches. So you need to understand what are the advantages and disadvantages on every approach, and you make your choice afterwards depending on what you need. Chapter 8 is actually quite heavy, and it deals with the calculation or the simulation of cables. So for the cables, we introduced the multi-conductor transmission line theory, which is an electromagnetic method, but it's not a full-wave electromagnetic method. So we explain a lot about the modeling of transmission line for cables. What are the circuit models were generated by a transmission line theory? How does the MTL solver actually solve? We talk about characteristic impedance and RLC of a transmission line. But then we discuss, I think what's quite interesting is 815 and 816, where we compare this transmission line models to full wave models. Because many times when I see publications, I often see people saying like this type of cable cannot be simulated in full wave because it's too complicated. Not always this is true. And many times you could simulate a cable if the cross section is not too crazy. You can simulate them with both, and you have to understand what are the limits of the transmission line method and when to employ a full wave method. Okay, so this actually, okay, this is I went a little bit ahead. It's 8-1 or 8-2 cable simulation full wave versus transmission line. I think that's very interesting. I never seen this in a book because people stick to the one or to the other. Here we are comparing them. Then we talk about common and differential mode, very typical topic you find in EMC books. We compare the emission from common and differential mode, and we discuss the generation of mode conversion by imbalance and apply this, of course, to the simulation methods. For example, if the simulation model is very, very symmetric, you will almost have no imbalance. So that means a perfect symmetric simulation model might deviate from what you measure in your lab, because in your lab the cable is never perfectly symmetric and contains some certain amount of imbalance, while in the simulation this might not be the case, and we discuss how to resolve this. We have an application example which is now a large. We have a cable of 30 meters in the wing of an aircraft, and we discuss now how this MTL, this transmission line models, can become also very, very complex in terms of circuit simulation and how to resolve this complexity. From up to here, there was all unshielded cables. Then we move on to shielded cables. We have an application example, crosstalk into a shielded wire, very much taken from what Clayton Powell is studying into his book. We showed that the transmission line can generate exactly the results you know from Clayton's Paul book. And then we try to discuss the shielding properties by introducing the transfer impedance, explaining the properties of a transfer impedance, and using the triaxial method for the estimation of transfer impedance. A short section in the end is actually the hybridization, where we can couple the transmission line to full wave solvers, bidirectional, but this is not done in detail. It's more kind of introduction, because we think that this topic is again very, very complex, and this cable, the cable chapter, as you can see, it goes from 370 to 376. It's pretty heavy already. There's a lot to say about cables. Finally, we have a summary of the transmission line theory, just to give you an idea how the solution works, very similar to what we did for the full wave solvers in the beginning. This is what we do for the transmission line theory. And another advance is the stochastic wire harness, where we have a wire harness which is not the same, right? Because it changes over the length, because cables change the position inside the wire harness. How to deal with such a case? It's more introductory at this point. We also don't go into deep examples, but we wanted to introduce that something like this is also possible to be done by simulation. The last chapter for today, chapter 9, is EMI filters. What we do with EMI filters? So I told you in the case where the shielding effectiveness was purely EM simulation. Now, when we talk about EMI filters, basically an EMI filter composed of discrete components, we are now for the first time bringing to, I mean, not for the first time, we did it in examples before. Sometimes the example which are shown in the earlier chapters, like for example, the coupling of the antenna, twisted wire pair into antenna. It's already a pretty advanced example, but we wanted to have some interesting example up front. Even not yet all the methodology is known at this point, but in the terms of explanation of the individual steps in the EMI filter chapter, what we do for the first time is now we bring together a full wave electromagnetic simulation and components together. Okay, so this is still only in frequency domain, because for the time domain, chapter 10, conducted emission, requires additional steps. But here we talk about such a comparison. We start doing the filter analysis via circuit simulation, very similar like what we did for the buck converter in the beginning, but then immediately couple it to our electromagnetic tool, right? And then we show how this coupled simulation can be used for filter design, and how some connection properties, not only the properties of the individual components, but things like, for example, grounding screws, how they affect the circuit simulation, okay? And sorry, how they affect the filter performance. So this is actually done in 9.5. I'm jumping a little bit because I'm explaining the book from my memory, how we did it. So this component investigation is done here. But before talking about this, a very important and a very subtle section is actually using the measured S parameters in electromagnetic simulation. Because sometimes you might measure a component, and you might measure the component in a different environment than you are using it in a simulation. And this is really subtle to know when we are describing this in detail. What happens if the measurement is, for example, done, this is a very common case, is the common mode choke, where a measurement is performed with a 4-port VNA over a ground plane, but then the measured S parameter block is used in a simulation where no ground plane is present. And we are discussing these cases because that's important to understand that you are measuring and you are simulating in a different environment, and you need to be aware that this might lead to errors. Talking about common mode choked, actually 9.6 discusses the EM modeling of inductors. Inductors are often large and they might couple with stray field, right? So from time to time, we would like to generate a 3D model of an inductor, while we maybe not have a validated model from the supplier. So here we talk basically about reverse engineering. We take our geometry and we tune the geometry and the material parameters to obtain the same response like in the data sheet of the inductor. So this is 9.6. And in 9.7, a more advanced topic is how we can model core saturation of inductors, core saturation due to a DC current and so on. This is again an advanced topic in case you are interested in this, but you might as well have skipped through it. So this is what I wanted to show you today. I'll be coming in a few weeks with the next step. I hope you have enjoyed and you are thrilled to read the book. You are interested in this content. Thank you very much for your attention. Have a nice day. Bye bye.